Hi, my name is Octavian, and it's 12 sharp. And you know what time it is? Lab time! Today I'm going to show you some properties of the aluminum metal, which has both metal and non-metal properties, being an amphoteric metal. Amphoterism is about the interaction of the given substances with bases as well as with the acids. And we are going to observe how the practical and the theoretical experiments are conducted. From the start, the aluminum has to be cleaned by its oxidative stratus that forms in order to prevent the interaction of the metal with the air moisture. In this experiment, I'm going to use the aluminum foil, whose oxidative stratus is very thin and dissolves well as in acids, so in bases. I will use sodium hydroxide and concentrated sulfuric acid. Firstly, I will take the sodium hydroxide solution, which can be purchased in any household products shop, with its marketing name Krot. From the label, we can make sure that there is sodium hydroxide and mineralized water. The proportions in this experiment don't really matter, because I want just to obtain the gas, not the solution. I will pour some sodium hydroxide into the glass bottle, and I'll add some aluminum foil spheres, tiny ones, in order to make the reaction happen. Okay, I will add 4 spheres, I think it will be enough, and the ending of the bottle will be sealed with a balloon. Okay, the reaction has started. At the same time, I'll prepare the sulfuric acid solution. It's around 60%. And I will too add some aluminum foils to it. Okay, as we can see, the balloon is starting to get bigger in the volume. So I've changed the balloon for the sodium hydroxide solution because it was not the convenient for me. Okay, the reaction between these aluminum foil and the sulfuric acid haven't started yet, but we can see that, oh my god, it's pretty warm out here. Okay, so we can see that the collected gas will be in the balloon, will result in the balloon, and I think the reaction have stopped. Okay, this is enough for me. And here I'm still waiting for the reaction to happen. Okay, so what is the trick here? In both the reactions, the obtained gas will be trapped into this balloon, and both gases are hydrogen. The hydrogen will remain in the balloon, but it will try to escape the room because it is lighter than the air. Where do I know that the collected gas will be the hydrogen? Okay, so let's move on to the table and I'll explain the chemical equations. So, what is really happening? The answer to that is in this equation. Aluminum in the solid form plus sodium hydroxide in an aqueous form plus water results sodium, aluminum, O2 plus hydrogen gas. Okay, so that's now clear. So this is a redox equation. So let's now balance it. Let me just write here. It's liquid, it's aqueous form, and this one is a gas. So the enthalpy for that is lower than 0. Okay, so the aluminum from the 0 oxidation state and the hydrogen from plus oxidation state change into aluminum plus 3 oxidation state because it's -2 Minus 2 multiplied by minus 2, it's minus 4. Sodium has plus, so the minus 4 plus 1, it's minus 3, so we need plus 3. And the hydrogen gas will have the oxidation state 0. Okay, what really happened? Aluminum from 0 turned into aluminum plus 3. So in order to that, it needs to give 3 electrons. Okay, I'll write that down. Minus 3 electrons. Then the hydrogen. 2 hydrogen plus ions become an hydrogen H2 gas with oxidation state 0. So in order to that, it needs to gain 2 electrons more. Plus 2 electrons. So at the start of the reaction, the aluminum metal was a reductant and it became an oxidant. And the hydrogen ions were an oxidant and the hydrogen gas became a reductant. Okay, so the process for the aluminum to change its oxidation state, it's called the oxidation process. The process that hydrogen changed its oxidation form is called a reduction process. Okay, now let's find the common multiple, the highest common multiple for both of them. From 3 and 2 is 6. So 6 divided by 3 is 2. And 6 divided by 2 is 3. Now let's equal the equation. Okay, so let's put 3 on the hydrogen here. Let's put 2 here. We will equal the sodium, it's 2 here, and the aluminum, it's 2 here. And in order to the equation to be equaled, fully balanced, we need to have the same amount of the hydrogen and the oxygen. We have here 2 hydrogen and 2 hydrogen. Here we have 6 hydrogen. So 4 onto 6. We need here to add 2. And the equation is balanced. And now the reaction between the aluminum and the sulfuric acid. So aluminum in the solid form plus sulfuric acid in the liquid form results aluminum 2 SO4 3 times in aqueous solution plus H2 gas, and the enthalpy of formation is lower than 0. Okay, now let's examine this redox equation. So aluminum had 0 oxidative charge and it changed to plus 3 because this ion is minus 2, minus 2. Okay, so then the hydrogen from plus 1 changed to hydrogen 0, hydrogen gas. Okay, let's write that down. Aluminum changed to aluminum plus 3. In order to that, I have mentioned that it needs to give 3 electrons, so it will do as well. And the hydrogen, 2 hydrogen plus, changed to hydrogen 0. In order to that, it needs to addition to more electrons. So how I have mentioned, the aluminum was in the initial state was a reductant and it became an oxidant, and the hydrogen was an oxidant and it became a reductant. So the process for the aluminum, again, it's called oxidation process. I'll write this in the short form, oxidation process. And the process for the hydrogen is called a reduction process. Again, the lowest multiple, the common multiple is 6. So again, 6 divided by 3 it's 2, and 6 divided by 2 it's 3. Now let's put that down in the our equation to balance it. So aluminum needs 2, here is 2, and H2, it needs 3 here and 3 here. So yeah, it's fully equaled. But someone could ask, what if as a result of this equation we won't obtain the hydrogen? So in this case, we will try to light the obtained gas and observe if it burns and eliminates a big quantity of heat, so it will demonstrate the presence of hydrogen. Okay, so the equation for this should be H2 in the gas form plus O2 in the gas form forms nothing else but water in the gas form. Okay, 1/2 OFC. The equation is balanced. So the thing is, why is here a gas? Because we all know that the water is liquid. But the thing is that the enthalpy of formation is so high. It is equal to 286 kilojoules per mole. It's indeed a big quantity of heat. So let's examine the amount of heat obtained as a result of the experiment. So we said that the enthalpy of formation of this equation is equal to 286 kilojoules per mole. We will consider that we took 1 mole of hydrogen, so in the result we will obtain 1 mole of water. The molecular mass of water is equal to 18 grams per mole. And if we consider that we took 1 mole into the reaction, the mass of the final product, so the water, will be equal to the nu of water, the n of water, multiplied by its molecular mass. The chemical amount is equal to 1, the molecular mass is equal to 18, so in result we will obtain 18 grams. Now we consider that we know the specific heat of the vaporization of the water, so lambda V is equal to 2.3 multiplied by 10 at the 6th power joules per kilogram. And we will consider that we know the specific heat of the water too, so C equals to 4.2 multiplied by 10 at the power of 3 joules per kilogram, multiplied by Celsius. Okay, so then we will write some formulas down. Q, it's the amount of heat, is equal to the chemical amount multiplied by the enthalpy of formation, 0. Okay, so then we will have that the amount of heat used on the vaporization of the water is equal to the mass of the compound multiplied by the lambda V constant, this one. And we'll write that the amount of heat that was used for the temperature changes is equal to mc delta T. Now we will equal that Q is equal to QV plus QT and is equal to m lambda V plus mc delta T. What I am going to do with this equation? So what I want to know is this delta T. It's the differences between the initial temperature and the final temperature. Okay, so we'll write that Q is equal to m, that m is the common factor, m lambda V plus CT, C delta T. Okay, then, okay, I'll clean this. We do not need this anymore. Then Q over M is equal to lambda V plus C delta T, where Q over M minus lambda T, lambda V, is equal to C delta T, where C delta T, or delta T only, is equal to Q per M minus lambda V, all of this on C. So if we put the values, it will be that delta T is approximately equal to 3,235 degrees Celsius. So this is the resulted temperature. It's delta T is equal to T2 minus T1, where T2 is the final temperature and T1 is the initial temperature. Okay, so just believe me or not, but at this temperature, I do not think that you'll find the H2O gas, H2O molecule. You'll find it in liquid form. Okay, so at such temperature, the water will turn from one aggregation state to another instantaneously, because the water boils at 100 degrees Celsius. We all know that. And now it's time to test this. So these are the results of the reaction. This is the sodium hydroxide and the aluminum one, and this is the acid and aluminum. It is still quite reacting, but we do not have so much time. I honestly expected more of this. I think it is we need to heat it. Okay, and the temperature is extremely high. Wow. Okay, I'll let this. I'll play with this one. So let's take the balloon off. Carefully. Now, let's make sure that the gas won't escape it. Unfortunately, the balloon has not so much hydrogen in it, so it cannot fly to the top, because the mass of the balloon is much heavier than the mass of the appropriate hydrogen. But honestly, the hydrogen is less denser than the air, so it will fly to the top of the room. Okay, now let's light on the hydrogen balloon. Of course, security technique first. Okay, so ready? Woo! Did you see that? That was amazing! Wow! So, thanks for watching and have a great day. Meet you next time. Bye.